Hello everyone, JCE Connect. So in today's lecture, I'll be discussing about the most economical rectangular channel section. So in my previous lecture, I already discussed about most economical sections. What are most economical sections, and to achieve a most economical section, what parameter needs to be considered, Church's equation and all we have discussed in my previous lecture. So here I'll be deriving most economical rectangular channel section uh, conditions for a most economical rectangular channel section. Uh, the most economical means here, as the term or the name itself indicates, economical means the cost of construction should be minimum. At the same time, the efficiency of channel section should be maximum. To achieve this one, the maximum efficiency at minimum cost, what are the conditions we need to get for the rectangular channel section? What parameter needs to be reduced to achieve a maximum efficiency? Efficiency means maximum discharge we need to get. So as we know, Q equal to A into V. So in this one, Q is the discharge and A is the area of channel section, and V is what? Church's velocity equation, C root of RS. So in this case, area of channel section is constant, then the bed slope will be constant, then the roughness of the surface will be the constant. So everything is a constant, since we are assuming this as a rigid boundary channel as well as prismatic channel. For a prismatic channel, the cross-sectional area remains constant throughout the length, bed slope is also constant, then the roughness of the channel section is also constant. So only variable we get here is depth of flow in channel section. So as the depth of flow varies, automatically the perimeter, that is wetted perimeter, also get varies. So how much perimeter or how much minimum perimeter we can uh, reduce to achieve maximum efficiency, or to achieve maximum discharge in a channel section. So we'll see in this derivation, that is rectangular channel section derivation. Okay, so for that, let us consider a rectangular channel section with a bottom width B and depth of flow as a y. Bottom width B and depth of flow as a y. That is as shown in the figure. This is B and depth of flow y. Since it's a rectangular channel section, the flow area can be written as A equal to B into y. Also, wetted perimeter. Wetted perimeter means the length of a channel boundary which is in contact with the water, that is called wetted perimeter. This side, and this side, that is y plus b plus y, that is b plus 2y, that is wetted perimeter. Substituting the value of b from the flow area equation, then we get this one. So as we know, to achieve a most economical channel section, the perimeter should be minimum, that is wetted perimeter should be minimum. For a minimum perimeter, the dp by dy, that is differentiating perimeter with respect to depth of flow. As I said, the only variable parameter here is depth of flow. So differentiating perimeter with respect to y, we get this condition, that is p equal to 2y. So that is width of channel section should be twice the depth of flow, or depth of flow should be uh, half the width of channel section. This is the first condition. And the second condition is hydraulic radius. Hydraulic, that is r equal to a by p. So here when you're substituting the values of a and p, so we will be getting r equal to y by 2. That is hydraulic radius should be half the depth of flow. So these are the two conditions where we can say the rectangular channel section is most efficient channel section by having these two conditions, this one as well as this one. So next, the next derivation is for the most economical trapezoidal channel sections. Again the same procedure, that we need to minimize the perimeter. If we minimize the perimeter, automatically we will be getting the maximum discharge, because the equation, as we know, Q equal to A into V. So in this, area is constant, bed slope is constant, the roughness of the surface is constant. The only variable parameter is depth of flow. So depth of flow is depends upon the perimeter, or the perimeter is depending upon the depth of flow. Hence the perimeter should be differentiating with respect to y. When we differentiate with respect to y, automatically we get the conditions for most economical channel sections. So there is a the conditions derivation is very easy. The only thing we have to remember how the perimeter can be minimized. So let us consider a trapezoidal channel section of width, bottom width B and depth of flow Y. Here bottom width B and depth of flow as Y or D. And also take side slope for a channel section, side slope 1 vertical to Z horizontal. Here you mentioned 1 vertical to Z horizontal. And if this is B, then this also B. Then how this has come, that is ZY, this and this. It comes, so let us take this as a X for one vertical. Here I mentioned, for one vertical, Z is the horizontal given. Therefore, for Y vertical, X is horizontal. Then cross multiply it. You will be getting X equal to ZY. So that is given here. So I given ZY here and ZY here. So I hope you understood. The side slope channel side slopes are given. That is for one vertical, Z is horizontal, and for Y vertical, X is horizontal. So when you cross multiply it, you will be getting X equal to Z into Y. Then next, then the area of flow can be easily written, that is A equal to B plus ZY into Y. How it comes? B plus ZY into Y. See, as you know, area for a trapezium, top width plus bottom width. Top width, how we get? B plus 2ZY. B plus 2ZY plus B, we are getting A, area of trapezium, B plus 2ZY plus B divided by 2 into Y, depth of flow. Then B plus B is a 2B, and here 2ZY. Take a 2 out. Then when you take 2 out, then 2 get cancels. You will be getting B plus ZY into Y. That is area flow. I hope you understood. Then this is the area of flow. Then the wetted perimeter. So wetted perimeter I already explained in my previous derivation, that is rectangle channel section. Wetted perimeter means the length of the channel boundary in contact with the water. That is this one this one and this one. That is bottom width of the channel and two side slants, length of two side slants. Then how the weighted perimeter can be obtained? B plus 2y root of 1 plus z square. Then also you may ask how this 2y root of 1 plus z square comes. So here the B, as you know, this is the width of the channel section. Then 2y root of 1 plus z square, how it comes? See. So this is zy, this is zy, and this is y. Then this one is 90, this is 90 degree. Then this side is hypotenuse. Apply Pythagoras theorem. Then when you apply Pythagoras theorem, you will be getting z square y square plus y square is equal to this one, that is AC. This is AC, this is AC, this is AC, AC square, so AC square. Then AC will be what? Root of z square y square plus y square. Then you will be getting y will come out, that is y root of 1 plus z square. So this side slant length y root of 1 plus z square, this side y root of 1 plus z square. You will be getting 2 times y root of 1 plus z square plus b. The same I given here. I hope you understood. This is b plus 2y root of 1 plus z square. Then from the flow area, just calculate b. You will be getting this one. Then substitute the value of b in the above equation. You will be getting this one. Then for a minimum perimeter, dp by dy is 0. So here you will be having a two conditions or two cases. Since we are studying prismatic channel sections, and that too rigid boundary channel sections, in the rigid boundary channel sections or a prismatic channel sections, area of flow, bed slope, and the roughness coefficient all are constant. The only variable parameter we get is depth of flow. So since it's a trapezoidal channel sections, you will be having two conditions. One is depth of flow and another one is a side slope. So here the two parameters are variables. One is a depth of flow, other one is a side slope. So here I am writing two cases will be considered. The first case is when side slope, that is z, is constant, depth y varies. Second condition is when side slope z varies, depth y constant. So either you may write this as depth y or d. Okay. So these are the two conditions needs to be considered while deriving the most economical trapezoidal channel section conditions. So here first case we will consider, that is when side slope is constant and depth of flow y varies. So here I am considering the first case. So in first case I will be taking when side slope z is constant and depth of flow y varies. So consider the perimeter equation here. So here consider the perimeter equation. So already above it is written, just consider that one. Then for a minimum perimeter, dp by dy is equal to 0. Just differentiate this equation with respect to y. As I said, side slope is constant, the variable is depth of flow. With respect to depth of flow, when you differentiate perimeter, you will be getting this one. So just rearrange the term, you will be getting this one again, substituting the values of a, then you will be getting this one. Just go on substituting the values or then the rearranging the terms, then finally you will be getting this one. Just to solve it, just so simple, just to solve it, and you will be getting this one. So what is this condition? This condition is very, very important. So what this condition says, b plus 2zy is equal to y root over 1 plus z square. So b plus 2zy divided by 2. So this is a trapezoidal channel section, and this is what top width. So top width, is it b plus 2zy? So this is b, then this top width will be b plus 2zy divided by 2. It means half of top width is equal to y root over 1 plus z square. So what we are getting here, y root over 1 plus z square. Y root over 1 plus z square means this one side slant length we are getting. Means half of top width should be equal to one side slant length, that is y root over 1 plus z square. That is the first condition to achieve a most economical trapezoidal section. This is the first condition we need to achieve. So hence I written here, for a most efficient trapezoidal channel section, half of top width is equal to the one side slant length. This is the first condition. Then next, the next condition is very, very important. So when a semicircle drawn for O with radius equal to the depth of flow will touch all the three sides of the trapezoidal channel section tangentially. So second condition is what? Here, by taking, just observe here in this figure, by taking, this is the top width, this is the top width. By taking O as the center, here O as the center, and depth of flow as, that is d or y as radius, then by taking O as a center, when you draw a circle, that is semicircle, like this, it should touch all the three sides tangentially. This side, and this side. Then only we can say it is a most efficient trapezoidal channel section. I'll repeat once again. When you draw a semicircle by taking O as a center on the top width of the channel section, then taking a radius as depth of flow, that is a depth of flow as a radius. Then when you draw a semicircle, it should touch all the three sides of the channel section tangentially. If it touches tangentially, then that particular section gives most efficient channel section. So this is the second condition. Sorry. That is same again. A semicircle drawn for O with a radius equal to depth of flow will touch all the three sides of the trapezoidal channel section tangentially. This is condition number 2. Then let us discuss second case, that is when side slope z varies and depth of flow y is constant. In this case, again let us take the same perimeter equation, P equal to a by y minus zy plus 2y root over 1 plus z square. The same equation can be taken again here in this equation. So since we are considering the side slope varies and depth of flow y is a constant, so instead of differentiating with respect to y, here we need to differentiate with respect to z, because the z is variable here. So when you differentiate with respect to z, so you will be getting this one. Rearranging the term, again you will get this one. Then finally you'll get this one. So squaring on both sides. So when you square it, you'll be getting z square is equal to 1 by 3 or z equal to 1 by root 3. Then in figure, so tan theta. So here, suppose this is a trapezoidal section, you will be having a channel side slope, that is 1 over z here. Z horizontal, I'll show in figure. This side, here, there, this one vertical, Z horizontal. So in this case, so this angle to be considered as a theta. So what is tan theta here? The tan theta we get opposite by adjacent, that is 1 by z. Tan theta equal to 1 by z, but z equal to what? 1 by tan theta we get here, 1 by tan theta. Then 1 by tan theta means cot theta. Cot theta. But already we know the value of z. It has come 1 by root 3. So that will show you 1 by root 3 here. Z equal to 1 by root 3. Then we get from the figure tan theta equal to 1 by z. Z equal to 1 by tan theta. Then z equal to cot theta. Cot theta equal to 1 by root 3. 1 by root 3 means theta equal to 60 degree. Okay. So the sides of the channel section, that is, should have angle 60 degree, and this is internal angle should be 120 degree. That is the meaning. So this is 60 degree. Yeah. So next, also we know that from the first condition, this is the first condition we are having here. This is the first condition. So in this first condition, substitute the value of z here. When you substitute the value of z here, so we will be getting bottom width b, 2y root of 3. 2y divided by root of 3. Then also the slant length L. Substitute the value of z here. Again you will be getting 2y root 3. Then from these conditions, so what we come to know, the bottom width of the channel section is equal to the slant length of the channel section. When these two are equal, when the sides are equal, so we get, that I'll show you, we get here, when the sides are equal, that is this b also same and this slant length is also same, that is we are getting p equal to L. So it means all the three sides are having the same length. Then for a most efficient trapezoidal channel section, half of rectangular hexagon. Most efficient trapezoidal channel section is a half of regular hexagon. So hexagon means 6 sides. So side 1, 2, 3 and 4, 5, 6. Okay. So in this, since the sides are equal and also this angle is 60, then internal angle is 120 degree. So it represents half of the hexagon. Half of the hexagon. So hence most efficient trapezoidal channel section will be a half of regular hexagon. So this is the third condition. Okay. So once again you take the flow area and go on substituting the value of B and Z, you will be getting area of flow as this one. Then perimeter, take the perimeter, again already having these equations with us, substituting the value of B and Z, you will be getting this equation. Then again hydraulic radius, that is R equal to A by P, substituting the values, then we will be getting this one. Then depth of flow, we are having a D equal to A by T. We have a geometric parameters, depth of flow intersection will be D equal to A by T, area of flow divided by top width. Then when we take this formula and substituting the values of A and T, we will be getting this one and this one. So these are the conditions for most economical trapezoidal channel section. So please once again you go through these derivations. So I already provided you notes, so please go through that notes as well as you follow this lecture and just refer this derivation and try to understand. Thank you.